Welcome to the deep dive.
Glad to be here.
So today, we're exploring the hidden architecture of modern science, really looking at the structural pioneers who build the foundations for those, massive world-changing breakthroughs.
The unsung heroes, essentially.
Exactly. And if I were to write a title and description for this deep dive, it would be Unsung Catalyst, Kenneth Trueblood and the Computing Chemistry Revolution.
Oh, I like that. Unsung catalyst.
Right. And the description would basically say we are doing a deep dive into the incredible legacy of Kenneth Trueblood.
An American chemist who fundamentally changed how we see the molecular world.
Yeah, living from 1920 to 1998. We are unpacking his trailblazing X-ray crystallography lab at UCLA, his computer-assisted chemistry, and his vital role in the Nobel Prize-winning discoveries of Dorothy Hodgkin and Donald Cram.
It's a fantastic summary.
Thanks. I tried to weave in all those key concepts, American chemist, UCLA chemistry, X-ray crystallography, Nobel Prize chemistry, just to really set the stage for you, the listener.
It definitely sets the stage. Because while that name might not be on the tip of your tongue, his work directly fueled multiple Nobel Prizes.
He completely revolutionized how scientists physically map chemical structures. So, okay, let's unpack this, because we are looking at a fundamental paradigm shift here.
We really are. It's a profound shift to examine.
A shift in how human beings understand the literal molecular building blocks of the universe.
When we look at the historical record of mid-20th century chemistry, we are looking at a field that was hitting a hard mathematical wall.
A massive bottleneck.
Yes, exactly. Trueblood's primary legacy is his pioneering work in integrating early computers to determine chemical structures.
Right.
And what's fascinating here is the intersection of raw computational power and abstract chemical theory. It happened at a very specific, critical moment in history.
Well, he was born in 1920, right? Meaning his prime research years aligned perfectly with the post-war dawn of the computer age.
Which was incredibly fortunate timing for the field of chemistry.
To really appreciate what he accomplished, I think we need to look at the immense friction of that era.
Oh, the friction was unbelievable.
Because before mainframes entered the picture, determining the three-dimensional structure of a complex chemical...
Locating the exact spatial coordinates of every single atom.
Right. Locating all of that was a punishingly slow process.
It was an absolute bottleneck. So the field of X-ray crystallography relies on diffraction data.
Okay.
You pass X-rays through a crystal, they scatter, and you capture that diffraction pattern.
But that pattern isn't just a simple photograph of the molecule.
Not at all. It is a highly complex array of mathematical relationships. To convert that raw data into a three-dimensional electron density map, you have to run thousands upon thousands of Fourier transforms.
Thousands of them, by hand.
By hand, or at best, with early mechanical calculators.
Which is just wild to think about today.
It is. Solving a single molecular structure could easily consume years of a scientist's life.
Years on one structure. And the margin for human error in those manual calculations must have been astronomical.
Oh, absolutely.
I mean, you could spend 18 months on a data set only to realize a dropped decimal point threw off the entire spatial model.
And that is the exact barrier Trueblood recognized and dismantled.
He saw these early room-sized computers.
Machines that were primarily funded and utilized for things like ballistics trajectories or cryptography.
In military applications, mostly.
Exactly. But he realized they were essentially giant matrix-solving engines.
Yep.
He understood that the computational power of these systems could be harnessed to execute the Fourier series calculations that were holding back structural chemistry.
So he didn't just use a new tool. He fundamentally altered the speed limit of molecular discovery.
He changed what was physically possible within a human lifetime of research.
And that acceleration is vividly reflected in his personal output.
Yes, the publication record.
The historical record shows Kenneth Trueblood published 140 rigorous research papers over his career.
Which is just a staggering number.
It really is. When you consider the sheer amount of time it took to prepare, execute, and validate even a single crystallographic study back then.
Right. 140 papers represents a massive, sustained generation of foundational knowledge.
Like, how does someone even produce that much?
Well, in the academic ecosystem, a single peer-reviewed paper in this specific discipline requires meticulous experimental design.
Flawless data collection.
Exactly. Flawless data collection, rigorous mathematical analysis, and then defending that structural model against the skepticism of other experts.
So to navigate that gauntlet 140 times requires a relentless work ethic.
And an incredibly systematic mind.
It also proves his computational methodology was highly effective. He essentially industrialized the discovery process for his own lab.
He did. But his impact scales up exponentially when you look at who else was relying on his computational architecture.
Right, his collaborators. Because he maintained long-term, high-level collaborations with Dorothy Hodgkin and Donald Cram.
And that is where the historical narrative becomes really compelling. Because both Hodgkin and Cram are Nobel laureates.
Nobel Prize winners.
Yes. And Trueblood's computational work is formally recognized as significantly contributing to their Nobel Prize-winning discoveries.
Which totally challenges the popular mythology of the lone genius, right? The idea of someone having a sudden breakthrough in complete isolation.
It completely refutes that myth. Major scientific breakthroughs are rarely solo acts.
He wasn't the one accepting the Nobel Prize in Stockholm.
No, he wasn't.
But he was the one providing the irrefutable structural proof they needed to validate their theories.
He built the scaffolding for their breakthroughs.
I love that phrase. Built the scaffolding.
Well, if we connect this to the bigger picture how scientific history is written, the individuals who design the frameworks.
The ones writing the code.
Right, writing the code and building the computational models. They're often the unsung catalysts.
The true unsung heroes.
Exactly. Hodgkin and Cram needed to see the precise atomic arrangements of highly complex molecules to understand their function.
And Trueblood's application of computing power provided that vision.
He processed the diffraction data and handed them the three-dimensional maps that proved their chemical hypotheses.
He was the definitive authority they trusted to process their most critical data.
Yes.
And what's amazing is he scaled that authority into a physical environment. He didn't just process data for a few elite collaborators.
No, he institutionalized it.
Right. He organized a departmental X-ray crystallography lab at the University of California, Los Angeles.
UCLA.
And that lab became the gold standard. It literally served as a worldwide model for other chemistry departments.
The phrasing worldwide model really speaks volumes about his operational vision.
How so?
Well, in the mid-20th century, setting up a crystallography lab was not a matter of simply purchasing off-the-shelf equipment.
You couldn't just order it from a catalog.
Exactly. It required inventing a new kind of scientific infrastructure from scratch.
Yeah.
You had to integrate delicate X-ray diffractometers with data pipelines that could somehow communicate with off-site mainframe computers.
So to make this relatable, it's almost like creating the very first modern commercial kitchen.
That's a great analogy.
Like everyone else is still cooking over an open hearth, bumping into each other, doing everything manually.
Right.
And Trueblood comes along and invents the modern prep station, the industrial oven, the entire workflow of a high-end restaurant.
And once he builds it, every other chef in the world decides they need to copy his exact blueprint if they want to stay competitive.
It sounds less like a traditional chemistry lab with beakers and fume hoods and more like setting up a modern tech incubator.
Or an advanced data processing center. That is a highly accurate comparison.
Because he had to manage all the moving parts.
He had to establish the safety protocols for radiation, the data management systems for punch cards or magnetic tape, and the standardized workflows that allowed multiple researchers to utilize these incredibly expensive resources efficiently.
He created an optimized ecosystem for structural chemistry.
So when institutions around the globe realized they needed to modernize their own chemistry departments, they looked directly at UCLA's operational blueprint.
Trueblood had already solved the logistical and infrastructural problems they were just beginning to face.
Which perfectly sets up the next major phase of his career.
Oh, absolutely. Because someone who can take the chaotic, overwhelming data of a diffraction pattern and organize it into a perfect three-dimensional molecular model
Is uniquely equipped to organize people and resources.
Exactly. Let's look at his leadership timeline at UCLA because it is an astonishing run of institutional stamina.
His administrative career is just as structurally significant as his scientific one, and it requires a distinct, highly specialized skill set.
So it begins with him serving as the chair of the UCLA Department of Chemistry from 1965 to 1970.
Which was a period of massive expansion and transformation for American universities.
Really heavily driven by federal research funding during the space race and the Cold War.
Right. Managing a flagship chemistry department during that specific window means recruiting top-tier faculty.
Managing multi-million-dollar grant systems.
Yes, and overseeing the construction of new research facilities. It is a role that demands intense focus and political acumen.
And his success in that role clearly propelled him higher up the university hierarchy. Because immediately following his term as chair, He was appointed Dean of UCLA's College of Letters and Science.
Serving from 1971 to 1974.
Stepping into the dean's office represents a massive shift in scope, doesn't it?
Oh, completely. As a department chair, you are advocating for your own discipline. You fight for chemistry.
Right.
But as the dean of a massive college like Letters and Science, you are suddenly responsible for balancing the competing needs of the humanities, the social sciences, and the physical sciences.
That's a lot of different personalities and priorities.
You are managing thousands of faculty members and tens of thousands of students.
It requires an ability to see the macro structure of the entire university.
Much like seeing the macro structure of a complex crystal lattice.
Wow, yes. You have to understand how all the disparate parts bond together to form a stable institution.
His mind was clearly suited for finding structural efficiency in sprawling complex systems. Whether it was a mathematical matrix or a university bureaucracy, he could identify the most logical, efficient pathways.
But the fascinating thing is he never lost his identity as a scholar.
No, he didn't.
Because after serving as dean, he was awarded a Guggenheim Fellowship for the academic year of 1976 to 1977.
The Guggenheim Fellowship is a vital detail to analyze here.
It's huge.
It is one of the most prestigious grants in academia,
Hmm?
and it is awarded strictly on the basis of prior achievement and exceptional promise for future foundational work.
So it's not a Lifetime Achievement Award for being a good administrator.
Not at all. It is not an administrative award. It is a validation of purely intellectual, scholarly power.
It gave him the latitude to step away from the administrative machinery and return to pure research.
And to have that kind of scholarly firepower validated immediately after spending years running a massive academic college.
It shows an incredible duality of talent.
It really does. And the university wasn't done utilizing that talent.
No, they were not. He was called upon to serve as the chair of the Academic Senate from 1983 to 1984.
Which is the ultimate faculty governance role.
You are essentially the chief representative and legislative voice for the entire faculty body.
Negotiating directly with the university chancellor and the broader University of California system.
That sounds intense.
It requires immense diplomatic skill and universally recognized integrity.
Because the faculty are voting you into that spot.
Exactly. The faculty only elects someone to that position if they implicitly trust their judgment and their commitment to the core academic mission.
And that trust is underscored by the final administrative milestone in his timeline.
Right.
Because after all of that, after being chair in the 60s, dean in the 70s, and heading the academic senate in the 80s,
He goes back.
he returned to serve as the chair of the UCLA Department of Chemistry again from 1990 to 1991.
That is a profound testament to his character.
It really is. To return to the departmental trenches, managing the day-to-day friction of lab space and teaching schedules.
After having operated at the highest levels of university leadership,
Yeah, it demonstrates a deep, fundamental loyalty to his home discipline.
his peers asked him to lead them again decades after his first term because his leadership was universally effective.
He spent his entire career building models. Computational models of molecules, physical models for worldwide laboratories, and organizational models for the university itself.
It paints a picture of a quiet titan.
A quiet titan. That is the perfect way to describe him.
The kind of figure who ensures the institution thrives so that others can make the front page discoveries.
Which is why institutions find permanent ways to honor that specific kind of foundational legacy.
Yes, they do.
Exactly 20 years after his death in 1998, UCLA cemented his impact. In 2018, the university created the Kenneth Trueblood Endowed Chair in Chemistry and Biochemistry.
With Neil K. Garg appointed as the inaugural chairholder.
Now, for the listener who might not know, what exactly does an endowed chair mean in this context?
Establishing an endowed chair is the highest academic honor a university can bestow to memorialize a legacy.
It's permanent, right?
It is a financial and structural commitment in perpetuity. The principal funding is invested, and the generated interest supports the research, graduate students, and laboratory needs of the chairholder.
For as long as the university exists.
Exactly. For as long as UCLA stands.
So by putting his name on that specific chair, UCLA is guaranteeing that Kenneth Trueblood is literally funding the next century of groundbreaking chemical research.
And appointing a highly respected chemist like Neil K. Garg as the inaugural holder sets the caliber of scholarship expected for anyone who holds that title in the future.
It's basically a form of institutional immortality.
The standards of rigor, innovation, and collaboration that Trueblood established are permanently woven into the financial and academic fabric of the department.
Every paper published under that endowed chair carries his legacy forward.
It's the ultimate tribute to a foundational pioneer.
It is. You know, when you look at the entirety of his life, what really stands out is the profound value of foundational structural work.
We naturally gravitate towards celebrating the final product.
Of course we do. The Nobel Prize, the new miracle drug, the revolutionary material.
But this deep dive illustrates that the individual who builds the infrastructure is the one who actually dictates the pace of progress.
He fundamentally altered the trajectory of chemistry without needing to be the sole face of the discoveries.
He saw the latent potential in early computing. He applied it to a massive mathematical bottleneck. He shared that methodology globally.
And he organized an entire academic institution around the pursuit of rigorous science.
His impact isn't just a footnote. It is the hidden scaffolding that supports modern chemical analysis.
He completely redefined what it means to be a catalyst in the scientific community.
Which raises an important question for you, the listener, to consider long after this discussion ends.
Yeah, I'd love to leave them with something to think about.
When you look at the massive technological or scientific breakthroughs making headlines today,
The breakthroughs in machine learning, quantum computing, genomic mapping.
exactly, who are the invisible Truebloods in the background?
Who are the people writing the base code?
Organizing the massive data pipelines and building the structural models that make those public triumphs possible.
The people who won't be on the magazine covers, but who actually made the work happen.
Right. Who is building the scaffolding today?
A brilliant perspective to leave off on. The individuals building the tools are often the ones quietly shaping the future.
They absolutely are.
Thank you for joining us on this deep dive into the legacy of Kenneth Trueblood. Keep questioning the structures around you, and we will catch you next time.